Okay, so we spent quite a while talking about optimization algorithms. Now, this week, I want to spend just a little while talking about another topic that comes up very often in kind of probabilistic machine learning and sort of machine learning and probabilistic inference more generally, which is decision theory. So what I mean by decision theory is just the question of how do we make decisions, how do we choose actions to perform in the real world. So we focused mostly so far on the case where we've observed some values x and there's some value y that we're trying to do inference about, and we have come up with a probability distribution, probability of y given x. And maybe we've parameterized that probability distribution, and we've used all kind of clever ways to figure out what those parameters are. But at the end of the day, we end up with a probability distribution over y. So the simplest example of this is when this is a classification problem. X are some features about our example, and y is our classes, cat or not cat, disease or not disease, or whatever else. The question I want to talk about now is, given that we've figured out this posterior distribution, how do we use it to make decisions about what actions we're going to perform? Now, I especially want to talk about this because I would say this is done wrong more often than it's done right. And I'll talk about a couple common mistakes that are made in doing this. So in order to make decisions, we need to have some sense of utility or loss. So by utility, I just mean the goodness of a given choice. That is, how much overall happiness in the world that's caused. Similarly, we can define loss as the badness of a decision. Now, notably, so we're going to define this using L. L is the loss of a given action when the world is in a given hidden state H. By the way, the textbook uses H here for the hidden state of the world, where we might have used Y in the rest of the textbook. So that's what we mean by H. It's worth noting that we've used loss as the negative log likelihood for most of the rest of the textbook. Here, we're specifically using loss as this arbitrary measure of badness. And the loss could just be positive when you make the wrong prediction, negative or a 0 when you make the right prediction, or higher when you make the wrong prediction than when you make the right prediction more generally. But it could have sort of a complex relationship with whether or not you make the right decision. So let's look at this example. Maybe we're trying to predict based on some kind of test or whatever, whether a patient has no cancer, mild cancer, or severe cancer, and we have to make the choice of, do we do nothing, do we give the patient drugs, or do we perform surgery? And we can figure out what the loss is, meaning, how much pain and suffering does the patient endure given these three actions in these three situations. So for example, maybe if we do nothing and the patient had severe cancer, well, it's really bad. The patient probably dies or whatever. If maybe the surgery is so invasive such that if the patient has mild cancer, it's just as bad to leave that mild cancer completely untreated as it is to do surgery on a patient with no cancer. Now, we have to define these appropriately, but the point being that based on the outcome of our actions, it may be important to not simply just use whatever the most likely prediction is and use that to drive our decision making. For example, maybe if we think there's even some probability that a patient has severe cancer, maybe it's worth going ahead with surgery just because the outcome is so bad if we do nothing. Okay, so we're going to look at a couple cases of, in practice, how can we use the results of some probabilistic inference. So here we're going to assume that we've already figured out what our posterior distribution is of H given whatever data we have, and we're going to figure out how we use that prediction from our posterior distribution. Okay, so let's start with the classification case. That is, there is some true value of y, either 0 or 1, disease or not disease, and we have to make some prediction of disease or not disease, y hat, and we're going to act accordingly. Now, in a lot of cases, like that disease prediction case I showed in the last slide, there are different costs associated with making a false positive, that is predicting 1 when the true label is 0, relative to a false negative, that is predicting 0 when the true label is 1. For example, if we have to decide whether or not to treat disease or not, it could be the case that maybe the treatment is not too invasive, but if we don't treat a patient and they do actually have the disease, they could have really serious consequences. So that is to say that the loss from a false positive is relatively low. We give them the treatment even though they don't need it, relative to the loss of a false negative, maybe death or whatever. We can work out what's the optimal decision. That is what minimizes our expected loss. That is, given that we have some posterior distribution over y being 1 or 0, which choice minimizes the average loss? And with a little bit of math, we can work out that we want to choose y hat equals 0 if the probability that y equals 1 is less than this. So this is the loss if we predict 1 when the true value is 0, and vice versa here. So you can see that if these two values are equal, then it's half that wants to be our threshold. But if there's a much higher cost to predicting 1 when the true value is 0, then we're going to have a much higher threshold for making that prediction. So one common way of displaying this is using an ROC curve. Stands for receiver operating characteristic for whatever reason. So this shows how our true positive rate, that is the number of things we correctly classify as positive, is a function of our false positive rate. Now, it's important to look at this whole curve because we might be choosing between different algorithms that have different characteristics. For example, in this case, algorithm 2 is able to achieve a reasonably high true positive rate with an extremely low false positive rate, where algorithm 1 can get a higher true positive rate, but only when we allow a moderate false positive rate. Now, the place where I think this is often done wrong is very often people will just show this curve and say, okay, well, looks like algorithm 1 is above most of the time, so we should pick algorithm 1. Or a very common thing to use is the AU ROC, that is the area under this curve, which is clearly higher, the better the performance is. So if algorithm 1 was always above algorithm 2, it would have a higher area under the ROC curve. But what that's essentially doing is it's saying that each false positive rate is kind of equally important. That's another way of saying that is we're not sure which false positive rate we're going to be looking for. So we're going to evaluate our performance according to the average of all those false positive rates. And I think that's almost never the right thing to do. Usually, when you're looking at a particular problem, you have some sense of what the relative loss is for a false positive versus a false negative. So you might be able to say that a false positive is maybe 10 times as costly as a false negative. Now, of course, there's probably some subjectivity or uncertainty about that, but I think almost never the right thing to do is just to use the AUROC and leave it at that. Usually, I think the right thing to do is to pick some reasonable values, maybe a couple of different reasonable values for the relative loss of false positives versus false negatives. Then for each algorithm you're trying to compare, find the actual value on the curve that corresponds to choosing that trade-off, and then say what is the expected loss in that circumstance. So I almost never see this done in machine learning papers. I think it's what you'll see almost all the time, and at this point, just because it's convention, you have to do this comparison of AORCs for different methods, but I think it's almost never the right thing to do, especially in cases like in medicine or biology, where often there are extremely different consequences of false positives versus false negatives. Another curve you'll often see is the precision recall curve. Recall is another name for the true positive rate. For whatever historical reason, in a precision recall curve, it tends to be the recall that goes on the horizontal axis, rather than in an ROC curve, it's the recall that goes on the vertical axis. No particular reason why, just convention. And then precision, which is true positives over true positives plus false positives. Precision is equal to 1 minus the false discovery rate. By the way, it's worth noting the difference between the false positive rate and false discovery rate. False positive rate is defined as false positives over false positives plus true negatives. So essentially, false positive rate is how many times you got wrong out of all of the things that are truly negative. Precision, or a false discovery rate, is how many false positives you got over all the things that you predicted positive. They have similar names, false positive rate versus false discovery rate, so they're often confused. That's worth noting explicitly. So precision is a useful quantity, particularly in problems where what a negative isn't all that well defined. So for example, maybe you want to find articles among all the articles that exist on Wikipedia that are about finance. So what you care about there, you don't care as much about figuring out which articles are not about finance. What you're going to give back from your search is a big pile of articles that you think are about finance. So you want, among that pile, you want not too many false discoveries. So that is to say, you want to have a high precision. Okay, so again, precision and precision recall curve is often what you want to look at in kind of search problems, and precision recall curve is another curve that's often used. Again, we can use the area under the precision recall curve, AUP PR, as a quantity. That's also called the AP average precision, where the average is over all the different possible recalls. Again, I think that's almost never the right choice. Very often, if we're doing some kind of search problem, maybe we're willing to accept a set of predictions only if that set of predictions is, let's say, 90% accurate. That is, we don't have any more than 10% false predictions among that set. So to figure out, so we just want the highest recall in that case. So to get that, we look at 90% on the vertical axis and go until we hit the curve here. So let's see, the curve looks like this. And then we get an answer, let's say 0.1 recall. Now, perhaps some algorithm has no recall, in this case, algorithm 1, it's this case, no recall that reaches that criterion. Well, if your user is only willing to accept predictions with some precision, then algorithm 1 is truly useless in that case. So again, I think using these kind of aggregate measures like AUPR, yes, they're used all the time in practice to compare different approaches, but I think they're rarely the right thing to do. Usually you want to figure out the relative loss of false positives versus false negatives, or you'll figure out what precision threshold you have to meet and figure out what does best. What gives you the best recall for a given precision threshold, or what gives you the best expected loss given relative loss of false positives versus false negatives. Let's look at another wrinkle that comes up often in classification problems. This is kind of my roundup of all the common mistakes that are done in kind of machine learning and making decisions using machine learning and evaluating machine learning. So this pitfall comes up in the case where there are ties in our prediction probabilities. So that is to say, if here are all our examples along the horizontal axis, it might be the case that all these examples with label A all received the same prediction probability. So this comes up often if, let's say, we have discrete predictions. For example, if we cluster and then we're using kind of that cluster indicator as our predictor, or if we have a set of examples, maybe a set of people, where we have some discrete feature, and that's all the information we have. So we don't end up having this kind of very granular, real valued prediction probability, but rather we just have, in this case, 4 different probabilities we get out. And for each of those prediction sets, A, B, C, D, we can order them into their probability of being a positive. So in this case, prediction set A has the highest probability. It has some, among that set, it has some true positives and false positives, and likewise for B, C, and D. Now, the pitfall here comes is, what if we're trying to compare algorithms that make different numbers of positive predictions? So in particular, let's draw this as an ROC curve. So if I draw what I just showed on the last slide as an ROC curve, we end up with a curve with basically 4 points, right? If we make just A our prediction set, we get this point here, a specific false positive rate and a specific recall. Likewise for B and C and so on. Now, there might be some other algorithm that has this as its set A. So the question is, which algorithm is better, or how do I choose among these methods? Now, the key insight here is that if we want more predictions than we get from just set A, but less than we get from set B, we can just take A plus some random subset of B, and that gives us kind of this larger set of positive predictions. So this is, I've written this as A at plus half of B. So that is if we took B, threw out half of it, and made that our predictions. Now, notice that once we do that, we trace out this line on the ROC curve, where we would get A's recall plus some extra recall due to B, and we get A's recall A's false positive rate plus some additional false positives due to B. And we can pick any line here just by using some fraction other than a half. Now, the nice thing about this is we can realize that this predictor here will always give us better approaches than if we use this other predictor A prime, because if we wanted, again, some intermediate false positive rate, we can just trace out this line. So the thing you'll see often, which is people will, when they have just some set of points, they'll linearly interpolate. That is, they'll draw lines between those points in their ROC curve. It's a intuitively reasonable thing to do. It takes a little bit of thought to realize, but we can do this we can realize that it's okay to do by making this observation, that we just pick some random fraction of our other prediction set. Here's the pitfall that I see very often in practice, and don't do this. So now how about in a precision recall curve? So again, here I've drawn the case where we have these points. What happens if I want to do A plus part of B? It turns out, and you can work this out yourself, it's not too hard to do, that if you add half of B to A, you get some point that, like we showed before, is A plus half, plus midway between A and B for recall, but some precision that is not equal to what you'd get along this line. So you actually end up getting a line that goes kind of down before it goes to the right. It's a convex curve to be most mathematically accurate. And in fact, it's a strictly convex curve. So you'll see this often in practice where people will draw straight lines between their points, and that's a wrong thing to do. And I've even seen papers where you're comparing two methods. So here we have I have my method that has these points A, B, C, and D, and here's the competing method. Let's call this one E. And the authors have drawn a line here between B and C and saying our method is strictly superior to this competing method E, where you could never get a predictor that gave you that performance. So in fact, it's not the case that the two methods are, or that this other method is strictly better. It's not obvious. There are some cases where the competing method is better, some cases where their method is better. Okay, how about for regression problems? These are cases where there's some true output y, and we predicted y hat out of, let's say, a linear regression algorithm. Now, there's some loss function that determines how bad it is if we predict y hat and the real value is y. So for example, maybe y is the optimal drug dose that a patient needs, and y hat is our predicted drug dose that we think the patient needs. Now, there's some loss function, and what we want to do, again, is minimize the expected loss. Now, again, it might not be some simple function. It might be that the patient does fine as long as the drug, you don't give them more than 1 milligram more than their true dose, but it can be as little as 10 milligrams less than their true dose, for example, or something funky like that. Here's a useful visualization of the errors made by a regression algorithm. And this is called the regression error characteristic, REC curve. It's kind of a continuous analogy to the ROC curve. So in this curve, we put some tolerance threshold on the horizontal axis. That is some difference between y and the predicted y that we're willing to tolerate. And then on the vertical axis, given that we tolerate that difference, what fraction of examples do we classify within the tolerance? And of course, if we accept zero tolerance, probably we're going to get zero things right within that tolerance. And of course, if we made our tolerance arbitrarily high, we're going to end up with all of the examples classified within that tolerance. And some algorithm might give some curve that looks like this. We can use this to compare different algorithms. For example, we might have some other algorithm that classifies many examples almost exactly right, but then the other examples it classifies like really terribly. It's just completely off the mark. So again, this is a useful way. I don't see this used very often in practice for regression problems, but I think it should be. It's a useful way of evaluating performance of a regression model.